trying to design, it won't have a way to look at an image, look at this graph of points and move a ruler around it. So it has to, it will only see numbers. So it has to represent the line as this ruler as also as some set of numbers. So this you might have seen already, right, in school, that any line that you draw on a graph paper like this, it has an equation. So you can write it as y equal to ax plus b. A represents the slope, so how tilted the line is, and B represents the intercept. So it's like so by changing B, you can move the line parallel to itself, but you cannot change its tilt. By changing A, you can tilt the line. Okay. So, and these two parameters, so that's where these parameters, so these two parameters are sufficient to describe any line you want. Well, not any line. So can you tell me one particular line that you might not be able to represent using this? Is there a line that I cannot represent like this? Yeah, this is a check that everyone is not asleep.
Sir, I
Sir,
have a
I think
small
for
doubt.
Sorry?
Sir, sir, my understanding is like the dots are not exactly in a straight line. So
Yeah, the
when the
dots are not in
machine
a
is,
straight line. Yeah, yeah.
so that is where the machine will be wondering how to make a straight line. So our goal is to teach the machine or to make the machine learn to find a straight line out of these not straight line dots. Is that
Yeah,
the goal?
so the goal is to replicate what students are taught to do in school, right? That move this ruler around, and when it's good enough, stop.
Okay, okay.
So at least the
Uh,
machine should be able to replicate what a student in class 7 or 8 is
yeah.
taught to
In
do
a
and is able to do. Yeah, yeah.
yeah. In a non-ideal situation, how the machine will be able to uh, uh, kind of do those adjustments?
Yes. Yeah.
Okay.
Yeah.
Okay.
But but I had the other question. So so I have written down these parameters and I said that, okay, our line will be like this, but is there a particular line that these parameters cannot represent?
Sir, can it be a 3D line?
No, in this graph paper. I mean, so all our lines are in this graph paper. We are in flatland. So
Oh, okay.
yeah, so maybe that's a good, so that's a homework to think about. So is there some line that this cannot represent? Okay, so but let's say we are only, so far we are happy with lines that are represented like y equal to ax plus b, and there, so now two parameters a and b. So given a and b, you get different lines. Given different a and b, we get different lines. And the machine's goal is to find this a and b, which corresponds to this best adjustment of the ruler. So now we have to define best. So what does it mean, best, right? I mean, so we were told to eyeball, like you eyeball this, and if it looks good or not. But what is this eyeballing really doing, right? So is this line, the one that is currently drawn, does that look good? I mean, does that look like a good solution to the problem? It doesn't, right? And why does it not? So I mean, this is an obvious kind of question, but it doesn't, because like if I take any particular value of x, let's say corresponding to this blue thing, this line gives me a value of y, which is somewhere. Yeah. So suppose I take this value of x, the line gives me a value of y, which is somewhere here, but the actual value is so far above. So there's a big difference. There's a big jump. But the jump could be on both sides. It could be here. It could also, maybe the line was somewhere, like maybe the line looked like this. Maybe the line looked like this. Sorry. Yeah, so maybe the line looked like this. Right. This also would be a bad line, because again, like there are differences. I mean, now the differences have an opposite sign. So here, this line is underestimating y, this line is overestimating y, but both are wrong, right? So neither of these look like a good solution. So here is one way. So like now that if you think about it, what one we can see, we see two things. So one is that yes, this differences matter. So for every x, for every data point that there's an x, we want the y value that this line predicts, that minus the x, to have small magnitude. It should not be very positive. It should also not be very negative, right? If it's very positive, then you are overestimating. If it's very negative, you are underestimating. So you want to avoid both of those. So maybe one thing we can do is try to give a score to each line. Okay. And this is the traditional way of doing this. So you define some kind of a score, more like a penalty actually in this case, for each line. So how do you define that? Well, exactly what I was saying. So basically you take for each data point, you have some line, some candidate line, which is given by these two parameters A and B. So you compute the difference between what is predicted, which is this. So this is what is predicted. And this is the correct answer. So you look at the difference between those. And again, since we don't care whether it's positive or negative, as long as it's large in magnitude, we are unhappy. So we square it. That squaring takes care of that. Right? So if you just square it, then if it's large positive or large negative, it becomes a large positive number. And this thing we would want to make small, right? Or I mean, often like if you want to think of it as score, then we put a minus sign in front, and then you would want to make it large. Right? Okay. So this score, the sum of squares, sum of squared errors, is at least some way for a machine, even a machine, to judge whether a candidate line is good or not. Okay. Is it clear? So this is, so in fact, like in all machine learning, going all the way to Chat GPT, etc., this is usually one of the hardest things. So to figure out how is it that you measure whether you have done well or not. This is often like getting this right is the biggest is the biggest jump in accuracy. So there has to be some way to figure out whether what candidates you have, whether what solution you have produced is good or not. Then maybe you can try to move to make it good. There's a question.
Hey Piyush, this is
Yeah,
Avinash.
hi.
Piyush, do you want to highlight as to, because since you mentioned about mean squared error, right? Do you want to tell the students maybe why absolute? Like that's an obvious question that I had when I first learned about it.
Why, actually that's a good, so that's a good, I don't know, like, because I didn't even want to talk about derivatives, but yeah, so like, so another thing, so what Avinash is saying is why square. I can put an absolute value, right? And that also should be fine, right? That is also good, and that should also work, and that also gives a score, and if that score is good, then also things are fine. It's so we have to think a little bit about why that is not preferred and why this one is preferred. And one answer has to do with the fact that if you draw a graph of the square function and the graph of the absolute value function, what do you see at zero? So the one thing looks like this, the other one looks like this. So I'm doing this cardinal sin of not drawing axes, but let's fix that. Yeah. Right. And this fact that it's smoothly varying is given a lot of premium, at least in practice, even in theory. But this fact that there is no corner is a pretty serious thing in practice. But I mean, we will not see why in the talk, but there's something to keep in mind. This is also part of the thing of like having a good way to measure whether you're doing well or not. So these many things that go into this measure. Okay. So is this clear? So this score, I just sort of wrote it down, but this is, you should think of this as a, like, you should question this and you should think about why only this, why not something else? Because as I said, very often this is the important thing, like figuring out how is it that you're going to measure whether whatever machine you're trying to make learn something is doing a good job or not. This measure is usually the most, or not the most, but it's one of the most important components in whether the learning will succeed or not. Okay, so learning in this case, of course, is to find the best parameters A and B, which in the end also look good, right? Okay, so with that, so we have the score. So now, given the score, we would all, of course, in this sense, we would want to increase its score because there's a minus sign here. So we want to increase the score. So we want to find out how the score would change if I change A and B a little bit. Okay, so how would the score change if I change A and B by a small amount? Okay, so is that clear? So if once we have that, then we can decide at least which way to move A and B. Okay, yeah. So now, so any questions so far? If not, I have a question. So how many people have heard of the term derivative? Like, or at least how many people have never heard the term derivative?
Sir, we have to choose A and B arbitrarily or something like.
No, A and B, the machine has to choose. It has to choose it so that its score is as good as possible. So okay, so I confused matter. So this is like, see, I didn't give a good score, and now I can't learn. So I wanted to ask how many people have not heard the term derivative, and now but I asked both questions, so I don't know whether the raised hands are of people who have or who have not. So let's say we decide on people who have not heard of the term derivative should raise their hand. Okay, so there are lots. Okay, so let's not talk about this. So it's a simple notion, but here's the thing. So you imagine that I take A and move it by a little bit. Okay, so I change A by a little bit, so by a very small amount, and then I measure how much does S change. So if I change A by 0.01, how much does S change? Like everything else remains fixed. Okay. So then I see maybe when I change A by 0.01, S changes by 1. Okay. It increases by 1. Right. Then I make the change even smaller. Maybe when I change change S by 0.001, and then I find that S changes by something quite close to not 0.1, but something close to 0.1. Not exactly 0.1, but close to 0.1. So then I feel as if, like, if I change A by something, S is changing by about 10 times that. Right? So then that 10 would be called the derivative. So it's basically the change in S divided by the change in A for small changes. Of course, it does not make sense for very large changes. It's only for very small changes. Okay. So this is like speed, essentially. So you find out these numbers for both A and B. So if I change A by a little bit, how much is S changing? So what's that rate at which S changes for unit change in A? What is the rate at which S changes for unit change in B? And these tell you the direction in which you should move, right? So what is the direction? So basically, if you see that, like, the rate of change of S is of a certain rate of change of S with respect to A is, say, 1. Rate of change of S with respect to B is 2. Then you change A and B in proportional to these. So why proportional? You have to think a little bit, but that turns out to work. So let's see. So let's see this thing in action, whether this works or not. And then this is still not fully specified because I said proportional, but proportional, when you say proportional, you have to say how much, right? I mean, so if it's 1, 2, should I move A by 1 and B by 2, or should I multiply 1 and 2 both by 0.01 and then move A and B by that much? That will also be proportional. So these things will matter. So let's see this in action. So here is this. So you can see this code, right? So what I have done here is I've generated some random data, basically, of the kind that was used to generate this plot. And now what we are going to do is to find. So this this thing here, this function minus grad. So this is what it is doing is it's computing a list of numbers, or so-called vector. So it's taking all the y values, all the x values. A and B are the same parameters as before, and it is computing these. So this v is the errors. So this is what goes into the S, the definition of S. And a little bit of calculation of the kind that I was just saying, that you change A by a little bit, see how much S changes, and change B by a little bit, see how much S changes, and look at the rate of change. That basically tells you that these differences, these derivatives or this rate of changes will look like this. So this, forget about this NP. One of them will be the mean of, like, you take the error vector and multiply each thing by the corresponding xi, and the other one is just the error vector, and you take the mean. That turns out to be the value. So this is, again, something you can try to do, or we can do it at the end to see how this turns out. So this is the direction in which we have to move. So then this step tries to move, and it has this parameter called enthusiasm. I call it enthusiasm. It's usually called learning rate, but let's not worry about it. So it's about how enthusiastic the machine is. So it has found that, okay, I have to move in this direction. So should I move a lot in that direction or a little bit? So we'll see. Maybe it looks like we should move a lot. It's a good direction to move. So let's move all the way in that direction. So that will be high enthusiasm. Low enthusiasm would be okay. No, maybe let's be conservative. Let's not move too much. We have learned a little bit already. So why destroy that? Let's move only a little bit in that direction. So and then we'll see which one is better. So by experiment. Okay. So then there's a little bit of code here, which is basically just going to apply these steps again and again and see what happens for different value of enthusiasm. Okay, so so let's just run this. So just go on. Yeah. So here is this thing with yeah. So the enthusiasm is 1 and number of steps is 7. So let's see what happens when you do this. So slowly the line seems to be moving, but in step 7, so this is looping, so you can't see it. But so after 7 steps, it's still not the best, right? Okay, so maybe let's say but it seems to be going in good direction. So maybe let's say we let the machine go for longer, and let's see what happens then. Oh, it still didn't do a good. Even in 30, it was like, sorry, additional months. Yeah. Yeah, that's actually a good answer. Like in 30 steps, it seems to have found something that is reasonably good. So this enthusiasm 1, and in 30 steps, it seems to have found a decent looking answer, right? I mean, I would not be unhappy with such an answer. So then we see it, oh, maybe we should be more enthusiastic. We should keep changing this mode. So let's make the enthusiasm very high, like 40. Let's see what happens now. Oops. Yeah. Oh, what went wrong? What happened to the line? Where did it go? So did you note? So let's see. So it started off well, and then it just moved very far to the other side because it was on this side, and this high enthusiasm made it move in this side, move it move to the other side. And then what happened here? Like it just moved again to that other side, but like by a huge amount, and now it's like turned back down. And this gets worse. Like now it's almost a vertical line, and now it's gone. So very high enthusiasm doesn't seem to help either. So, okay, so now we are chasing. So we maybe move to, like, say, something like 8, enthusiasm 8. Oops. Yeah, let's try again. Oh, this seems to have worked perfectly. Like it got to some place and then it got stuck there. And you see that this penalty got stuck at some 5.63 and refused to budge from there. Okay. This is one of the happy situations in like this linear regression thing, in which this method, if you choose the enthusiasm carefully, not too high and not too low. If you choose it too low, then you might just have to work for a very long time. If you choose it very high, then it might just not work. But if you choose it something in the middle, and how big that middle is, you can determine from theory, then you're guaranteed to converge. So this word you will hear very often, converge, in the sense that convergence is exactly what happened here. It got to a value of the penalty, and then the penalty stopped changing, and the answer is sort of correct also. So convergence just means the penalty has stopped changing. Here the convergence is to a good answer, because the answer where the penalty stopped changing was also a good answer. Like this line that you see, it's clearly, I mean, like this as good a job as one could do, right? So the linear regression has nice properties in this way, that like that all the problems that you see in general learning of deciding what the parameters
Excuse me,
should
sir.
be. Yeah.
Sir, I'm having one doubt.
Yeah.
Does this penalty can reach zero?
Sorry, what? Uh,
Does
what
this
can?
penalty number
Yes,
can reach zero?
good question. So can yeah. So actually, let me ask you back. So in this example, can it ever reach 0?
Like if we are talking about a straight line, it's kinda impossible, but a bit curves and these this might be.
Oh yeah, that's a
possible.
good idea. So that again we will come back to later. So yeah, you said correctly that with a straight line in this example you can never reach zero, right? The only way to reach zero is if the points, the blue points, all lie actually on a straight line. Then only you can reach zero. And here they don't, right? We can see that they don't. So here you can never reach zero. So there will be some positive minimum. Okay, so that's one thing. The second thing you suggested is that we can have a curve. Why have a straight line? We can have a curve, and like maybe by having a strong enough curve, let me just share the right picture. Yeah. So by having a like a curve that goes like so, or maybe like we could even try to do this curve, right? Why not do this curve like this. So, and then you have learned perfectly, right? I mean, you have fit the line. What's more to do? And we are done. Like it's a perfect fit. Penalty is zero. What can be a possible problem with this? We'll come back to this again, but maybe even already at this stage, you can say. So, what's the problem with doing this? So, yeah, anyone was
Not enough data.
I mean, yeah, so, but in what sense? I mean, what does not enough data mean here? So, I mean, yeah, you're related. So the thing is like, why do we do this fitting and all this, right? It's not for the sake of it, right? So the reason is that India, you will want to do prediction. After I fit this line, if someone came to me with a different value of X, or after I fit the line for a particular resistor and someone came to me, oh, now if I apply this voltage to this resistor, how much current will flow? And that voltage I have never measured, I can still use that line, say, oh, this should be the current value. And with high, like, I mean, I would be correct with reasonable accuracy. That's the point of fitting. That whole purpose is lost when you do this, right? Because some small noise, some small change here can now, like now it will, now because this curve will probably go like this. And so it's predicting something. I mean, the right thing, that should look a bit like this. So it's predicting something very weird. And the reason is that if you do this, you're fitting to the noise, you're fitting to all the idiosyncratic things that are happening that caused your points to actually deviate from the ideal thing. And these do not have like a good mechanism. So you're fitting essentially to something which does not have a good mechanism. And so you're moving far away from the thing that you are actually that you wanted to predict. And so your prediction would have a problem. So we'll see this thing happening in more detail later. This phenomenon is important enough that it has a name. It has actually several different names in several different fields. In this such situation, it's called overfitting. In this special situation of having polynomials or things like this where you curve, it's called the Ranja phenomenon. And this fact that if you fit it like so, this I mean, I very confidently do this curve looks like this. That's actually something you can almost prove, that if you take such polynomial curves and you constrain them in a small window to fit to such noisy things, then outside they sort of blow up. The fact that their freedom was restricted in this small thing makes them completely blow up right outside the interval. So this overfitting will cause big problems right outside the part where you have fit your data. And so this is another problem that you always have to think about in machine learning or any kind of learning, that you should not have a model that is so powerful that it can fit to the noise, because then it will just fit to the noise and then it will not be able to do anything on new data. So it should have enough power to do all useful stuff, but not so powerful that it just learns all the noise in the data. Okay. Any more questions? Okay, so this took quite a while. So now let's go to the next cousin, which is maybe more might look more like a usual neural network. There's a question about that a bit earlier. And this is a different task. So far our task was to predict numbers, right? So we have like this current voltage curve, and you're trying to predict the voltage for a given current or a current for a given voltage. Now let's try to do some kind of a more classification type thing. So this is like the kind of thing that you might do in a school biology lab. So you get some flowers of different species, and you want to say which flower is that? Which flower is that? Right. So this is classic data set. I mean, so this problem has been a staple of statistics for a long time. In just specific this form, and there's an old data set. So I think George Anderson was a botanist, I think, in the United States in the 1920s, who collected this data of 150 iris flowers. And these iris flowers were from 3 different species: so Iris setosa, Iris versicolor, and Iris virginica. And for each flower that he had, he measured just 4 numbers. So the length and width of a sepal. So does everyone know what a sepal is? So this iris flower looks a little bit like this. The colored thing, this thing is the petal. That I think is a more common thing. The sepal is the greenish leaf, which I mean, it's not probably visible here below this. So at the base. So yeah, so he measured basically the length and the width of a sepal, and the length and the width of petal. But already at this point, you should ask a question. I mean, like, you look at this flower. What does it mean? What is the length and width of a petal? Where should I measure the length? Should I stretch it a bit? Should I just curve a string around it? So already these things are a little bit. I mean, so you can imagine now how this will show up. This will show up in the points not actually being very accurate. I mean, you cannot take a number there and think of it as like I don't know, think of it like speed of light or something, which is like a fixed constant or something. It's not that. It's some noisy number where a lot of subjectivity is involved even in measuring it. Okay. But okay, so we have these 4 numbers per flower, and then the question is that is like, it's very reductive. I mean, so each flower is reduced to just 4 numbers. So the length of its sepal, width of the sepal, length of the petal, and the width of the petal. And the goal is for a machine to learn a rule to take these 4 numbers and classify from this which of the 3 species it is. Okay. So yeah, so that's the goal now. Is the question clear? So there'll be some data of these 150 flowers. I'll show how this thing looks like, and then the goal is to find out just from these numbers which flower it is. Yeah, yeah, there's a question. Yes, Akash.
Yes, Piyush. So,
Yeah.
like, I have a live question, like, how does one figure out that, like, these are the important attributes that are kind of relevant for my recognition problem?
Yeah. So yeah. So again, that's another yeah, like you don't. So it's more like you see if it is sufficient. If it works out, then sure. Otherwise, I mean, okay. So the right answer would be something that, like, your method should be such that if the data that you have is not sufficient, then it should detect that.
I see.
Yeah, right. I mean, so you should not be so powerful that you just fit the noise and get something. So somehow your statistical method should be such that if this is the problem, that your data is just not sufficient for answering the question you're asking, then this you should be able to detect, probably in
I
bad performances. Yeah.
Okay, thank you.
Yeah. Yeah. More questions?
I also had a question.
Hmm.
I wanted to ask, so could we use a teacher set, like with already solved answers to train the model that we're
Yeah,
going
yeah.
to
So in this case, yeah. So that's what we are going to do. So I mean, like, yeah. So of course, otherwise, how does the model learn, right? So in this case, what you will have is that, so this data is there, right? In that data, it's labeled. So what we will do is that we will take some part of the data which is labeled, so that the model knows that, okay, this flower with this sepal length, this sepal width, this petal length, this petal width was setosa. This flower with some other sepal length, some other sepal width, other petal length, other petal width was virginica, and so on. So it has these things. Based on that, it has to come up with its rule. And then that rule should be good enough that it should work also on new data that is different from what it was trained on. Right? Again, it's the same question of prediction. So it's not enough just to do well on the data you have already seen. The important thing is to be able to do well on data that you're going to see later, that you have not seen so far. Does that answer the question? Okay. So yeah. So then let's go ahead. So yeah, so the idea is to go from measurements to some learned rule, which will give the species. So we'll actually look at a simpler version of this question, because then it's easier to visualize the thing. So we'll not ask to do this three-way classification. We'll just say, I want to decide whether it's setosa or not. Okay, and also I will neglect some of the data. I will only look at the sepal length and the petal length. So I will ignore the widths, just the sepal length and just the petal length. So now here's the data plotted. So so the blue points are the setosa flowers and the green points are the not setosa flowers. So if you had to do this, what will you do? Like, what will be your rule? Does anyone have a candidate rule? Yeah.
So likely choosing between this 150 flower that which are setosa or which are other species, we can look about their appearance because if they will be from same species, they will have something common in them.
Yeah, that is true. But like this machine has already forgotten all about the flowers, right? So all it knows about the flower is its petal length and sepal length for now. It even has forgotten the width of the thing. So just from this, it is trying to. So yeah, it's a very weak machine. It's only trying to detect whether this flower is setosa or not, just based on these two numbers, the sepal length and the petal length. And here is a picture of like some measured sepal lengths and petal lengths. The green ones, so the colors are visible, right? Green and blue. I think they're, yeah. So this green ones are not setosa and the blue ones are setosa. So I think many people have suggestions on what their rule would be to separate.
So
Yeah.
likely if we see that for all the species, there is one thing common that their ratios are a bit different. Like if we see about the setosa, the sepal length is longer, but the petal length is smaller. So by calculating that ratio, we can figure out something.
So good. Yeah, ratio would be one rule. Does someone have a simpler rule?
Sir, we can see that for Setosa, the petal lengths are lower than 2.5, and for not Setosa, they're more than 2.5.
Yeah, good. So you're right. So you'll say is the petal length bigger than 2.5,
Yeah.
right? Something is that you do. So geometrically, how will you represent that? Like you will draw this line, right?
Yeah.
And you say everything above this line is not setosa, everything below this line is setosa.
Yeah.
Right? That's so this is what we would like our machine to do, right? So the machine cannot sort of see this picture. I mean, it can see this picture in some way, but like it somehow has to get to this point that it has to find some such line that separates the two. Okay.
So we can what we can do is also we can create like regions. Like instead of just one simple line, we can bound a region by like let's say two lines. We say two.
Yes, good. Yeah. So something like this, right? So we can do like this and say everything here is setosa,
In
everything
this
outside is
region,
also.
in this region, whatever you find up close to this region, that's setosa. Otherwise, it's not.
Yeah, good. Yeah, these are all very nice suggestions. Yeah, so and they're all like foundation basis for different machine learning algorithms. So we will see what problems can arise with this more advanced method of like having a region. But that's for later. That's a good answer. Any other suggestions?
Sir, we could also use the fact of both of the coordinates that for Cetrosa, they are averaging at around sepal length of 5 centimeters, and none of them have a petal length of larger than 3.
Yeah.
And
yeah.
for not Cetrosa, it's larger than 3 and a mean of 6.25.
So you're thinking of a region like this, right? Like something of this kind.
Yes.
And you say on this, yeah, okay, yeah.
But I don't know if this way is efficient or not, but we can, let's say we have a sepal length and petal length, we graph it on the graph and we compare all the distances with the other graphs and see which distance is the closest. And we can check whether the closest one is of which type, and most probably that will be the type of the flower.
The closest point. Yeah. Actually, yeah. So this algorithm has a name. It's just called nearest neighbor decoding. Yeah. So yeah, that's also a good answer. So it can, yeah, as you said, it can sometimes be not very efficient. because you have to go over the whole data set and try to compute distances, or at least some large part of it. But it's in some situations it is the right thing to do, and yeah, it has even a name. It's called nearest neighbor decode. Okay, so but let's see. So let's in the interest of time, let's temper our ambitions, and let's say our goal is for our machine to just learn this line for now. Okay, is this, yeah, okay, now, okay, so this is what we want to do. So here is so this thing has a name. I mean, it's called perceptron, and I just wanted to write this. Sorry, I don't know why there is so many things written here. Yeah. So this perceptron, the name comes from a paper written by someone who was in the aeronautical laboratory at Cornell University, and who was writing a paper in a psychological review. And this paper was about a probabilistic model for information storage and organization. So you can see that there's no division. Like, it's not like there are certain things that have to be only be studied in a certain field or something. So here is a person who is working in an aeronautical library writing a paper about probabilistic model for information storage in a psychology periodical. So that's also an interesting thing. The name perceptron also has become interesting. But here is what the perceptron, I mean, the perceptron is really, like in this case, just this linear separator. So I want to find this line which will separate the two. That the perceptron is a fancy name for that. And also for, I mean, the name also these days applies to the algorithm that does this finding. So here is what that algorithm looks like. So it's actually not so different from what we did earlier. So yes, so this is just some setup. The final the algorithm that that actually does this is following. So again, our line has to be, I mean, the line is always written as, so now actually our line has a better model. It's not written as y equal to mx plus c. It's written as ax plus by plus c equal to 0. That's also a valid equation for line. Any line can be written in that form. In fact, this one has the advantage that any line, really any line can be written like this, unlike the previous one. So there's an exercise that some lines cannot be written like that. Here, any line can be written like this. So these weights, so here there's a variable called weights. So this is a and b, so ax plus by. So whatever multiplies x and b, that is what this weights is. And this intercept is the c. So the c, so ax plus by plus c. So this x, this at symbol weights plus intercept, what it is doing is that it is taking all of, so like for every flower, I have these two numbers, right? So that are the x and y, like the x1 and x2, let's call it x1 and x2 for each flower. So it's making this so ax1 plus bx2 plus c, and it's making a list of all these things. So those are the scores in some sense for all the flowers. And the goal is that if the score is positive, I will call it setosa, and the score is negative, I will call it not setosa. Okay. So that's the thing. So one side of the line, which is where ax plus by plus c is positive, is the setosa side. Where it is negative is the non-setosa side, and equal is the boundary. Okay. And so what do? We first compute these errors. So the errors are basically those places where the algorithm was wrong, where the current values of A, B, and C, the weights and the intercept, were wrong. So what would wrong mean? Wrong means that the correct answer was, say, +1 and I was saying -1. So the correct answer was setosa, I was saying not setosa. Or the correct answer was not setosa and I was saying setosa. So that means that the product of these two things is not equal to 1. Right? So that's what this thing is computing, this errors thing. So this is basically those flowers for which we got it wrong. So what does the perceptron do? The perceptron just does the following. It takes, so this thing is just finding one of the flowers where you got it wrong. So this error index is one of the name of the flower that got it wrong. So we have that flower. We have the flower. And what do? We just do the kind of obvious thing. So we just take the values for that flower, the x1 and x2, and move the weights in that direction. Now, not exactly in the direction, but we have to also see whether we want it to be positive or negative. So we multiply by the label. So this y is basically whether we want it to be +1 on this flower or -1. That's the correct thing that we want. And we just do, otherwise it's the same thing. So we're just taking taking the x1 and x2 and moving the weights by that in that direction, right? And the intercept by just the label. And then there's also this, again, the same enthusiasm thing. How enthusiastic are we? So like we have to move in this direction, but how much do we move? That is what this enthusiasm is. Okay. That's the perceptron, and it will keep doing this until it finds an error. When it has no errors, it will stop. Okay? Because then there are no errors, it has found an answer, and it's good. Okay, so here let's try to run it with different enthusiasms. So what I will so what I will do is I will run it with few different. So I will start off with random line. So some line that is chosen at random. So that is already chosen here, and now we will just choose different values of the enthusiasm to see what happens. Okay. So here is the thing. So this one says that in about 17 updates, it managed to find the right answer. So let's see what that picture looked like. Yes, it will take some time to do the graphics. Yeah. Okay. So here is what it looks like. So the line right now is not even visible. It's some random line. It's in some other part of the plane. But what this pink point is the pink point that is a point that the line is, it's one of the points. Right now, everything is probably classified incorrectly, but this is one point the line is classifying incorrectly. So you use that point to move the line. So we move the line a little bit. So line has moved a little bit towards that point. So good. So now here is a point that it is moving incorrectly. So we moved it. Okay. It's not that the point is correct again, but the line has moved towards being correct on it. So that point again becomes a trigger and the line moves again. But now it seems like it made a problem, made the line go away in the wrong direction. So we do one more. Oh, now it has come back. Now it has gone again wrong. Again, something wrong. Again, yeah, it looks like maybe it's too enthusiastic, but slowly, yeah, and here it is. There's one problem that it's sort of on the edge, like it has found this one point almost on the edge, but otherwise it has found a line. So again, let's see what can we do by changing the enthusiasm a little bit. So let's change the enthusiasm from 10 to 0.01 and see what happens. So now it took a long time. So it took 40 iterations or something to do something to converge. But it's not like, notice that I went from 10 to 0.01 and it only changed from 17 to 40. So there is some advantage to having, like, it's not like it changed by 100. Like I would have thought that maybe one could have thought it could change by 100 because I'm less enthusiastic by a factor of 100. And but that's not what's happening, because the point is that it will not now lose things so fast. So right now it's like all these points, like it's moving very slowly. Like this point is just that. Yeah, now the line has come in the picture and now it is slowly going to adjust. And it's going to find probably a very different line. Yeah, it found a very different line. But notice that the advantage of having this small enthusiasm was that it took some time in the beginning to come to a decent answer. But once it got to a decent answer, it did not stray, unlike the previous one. Right? And so again, so in many applications, people would often have this enthusiasm or learning rate changing slowly over time. And again, this is again one of the arts, like people have to figure out how to change this over time. So we'll not do that. We'll just stick with one. So let me do just one more example with something in the middle. So we had 10 and then we went to 0.01. So let me do with it with enthusiasm 1.
Yes,
something in the middle. Sorry. Yeah. Please go ahead. Yeah.
so likely you said that if the value will come in the equation, you said that ax1 plus by1 plus c equals to 0. So if the
Yes.
value is positive, we are accepting that that flower is setosa, and if it is negative, we are not accepting that result. But what if the result is coming 0?
Yeah, so then we don't. Yeah, so this is again. So you just you can decide one convention and stick with it. So really, like what you want is to be really positive and negative. So in this thing, I'm taking 0 as not setosa, I think, if I remember correctly. But yeah, you stick with your yeah. So your goal is usually to find these kind of things which will not answer 0 on the things where you're interested in, because then even small changes can cause problems. Okay, so we already saw several things. So we saw like this importance of choosing how to measure we are making progress. This notion of enthusiasm or learning rate, like how quickly should you change your parameters in response to new data. If you change it too slowly, then in the beginning, especially, you might take too long to get to a decent solution. If you change it too fast, then you might come to a good solution and then stray away. And or some, like in the regression case, we found a situation where you just strayed away so much that you could never come back again, right? So again, all of these problems, they are not specific to these two simple examples. They happen in more yeah, they become even more pronounced in bigger models. So with that, let me actually look at something in the middle, which is like, so we saw like all the models we have seen so far had like 2 or 3 parameters. But before that, let's hear something to think about. Actually, this was someone asked a question also about this, that what we did was we put a line in between and the line was separating it. Another thing could have been to actually, like, not even just this region, like just take these blue points and draw this like very tightly fitting curve around it, which just sort of touches all these points, and say, if it lands here, I will call it Setosa. If it does not land here, I will call it not Setosa. And again, homework is why or why not should you do this? So maybe something to think about is what might be some problems with doing this. Okay, so let me say one thing. So this perceptron look like, okay, it's just one line. What can it do? So it turns out that a lot of the neural network progress happened by just stacking perceptrons on top of each other and beside each other. So bunch of perceptrons working together and then perceptrons on top of perceptrons. And this looks, maybe sounds complicated. It's not so complicated. And it can do things like detect digits, like one of the standard exercises in any machine learning course that you might take is this something called this MNIST example, where the goal is to detect some digits. So what you have is pictures of handwritten digits that look like this. So for example, this is 7, this is 2, 1, 0, 4. So this is and they're labeled. And what your goal is to train some machine learning model that looks at this picture, takes this picture. I mean, the picture, of course, is implemented, is now given to it as a bunch of numbers, like a file, and it has to output the digit. Okay. What it actually does is it outputs a probability distribution over digits. It says that, okay, maybe with so much chance it is this, so much chance it is this, something like this. And maybe the highest chance is what you take at it as its answer, and you want it to do well. Okay. So it turns out that yeah, I will not go into the detail of this because I'm running out of we're running out of time. But it turns out that you just basically take 2 layers of perceptrons. So there's some perceptrons that look at this image, whole bunch of them, actually 1024 of them, and then 10 other perceptrons that only look at these 1024, the outputs of these 1024. And these 10 perceptrons, basically each of them say they give an opinion. So the first one is supposed to give an opinion on whether it's 0, second one on 1, third one on 2, and so on. Okay. So 0 to 9, all digits. And whichever one is has the highest opinion is taken as the winner, and you say that this is my answer right now. And you train your model to do well with just this structure. So just a bunch of perceptrons. Okay. And here is what that training looks like. So let me just actually run the training. So here is what this model looks like. So it has, so this is like, now this has more respectable number of parameters, or maybe less respectable number of parameters. Instead of 2 or 3, it has like about 8 lakh parameters, this model. It's about 3 MB in memory. So it's still very small. And it looks a little bit like this. That's what I was saying. So it's like there are some perceptrons, like 1024 of them, and then they are remixed with by these 10. So here, let's do this training, and I am not going to say what this train thing means, but here is how I train, and let's see what happens. So let's look at it, this thing training, and you notice that this is slow, right? It's saying that it will take 37 seconds to just compute one epoch. One epoch is basically looking at the whole data once. Okay. Yeah, so this is slow on my computer. So let's run it on a more powerful computer on the cloud. And this particular computer is something called T4 GPU, I think. Yeah, T4 GPU. And let's see how, like, what the corresponding numbers for this look like. I mean, the model, etc., is exactly the same. So all I will show is this. So yeah, so let's just wait for this thing to warm up and start. Yeah, now it is starting. Yeah, good. Yeah. So look at this. Yeah. So this one was taking what? It has finished one epoch in 58 seconds. This guy finished one epoch in 7 seconds. So there's a race. 6 seconds, the second one. The third one in 5 seconds. And this one is still stuck at the second one. 0 seconds, 5 seconds. Yeah, so what suddenly, like, what's so fast about this computer? What is this T4 computer, right? But yeah, let's let it run and let's see the answer first, and then we'll look at that a little bit.
Sir,
Yes.
sir, I have a question.
Yeah.
We can get different perceptrons. In the last example, we got like two different
Yeah, two
perceptrons
different
per.
answers. Yeah.
Yeah. So what are the ways? Do we different initial conditions and different enthusiasm? Is there any
Yeah.
other way to get different perceptrons?
Yes, I mean, for example, in this algorithm, I said that you pick one wrong point and you use it to move, but there can be many wrong points. So which one you choose can also affect that. So at each point I said that there's this one highlighted point that was wrong, and the line used that to move. But there are many at any point. There might be more than one wrong points. So which one you choose can also affect your final answer.
Doesn't it lead to a huge number of perceptrons because then
Yeah,
we just saw
yeah,
two.
but yeah, we just saw two, but that's fine in the sense that, like, I mean, as long as it works, it's fine, right? Like, in the sense that any perceptron that is correctly classifying is good for us.
Okay.
So in all of these, yeah, there may be many solutions. Each one of them, any one that is good is good. So okay, so let's come back to this thing. So here is one interesting thing that I would like you to check. So here, what we did here, what I also did here is another thing is that, like, so as this thing trains more and more, so it looks at data more and more and tries to adjust its parameters. We track two things. So this x-axis is how many epochs, so how many times it has looked at the data. This blue points are its training accuracy. So the training data, how well is it doing? What fraction of the digits is it classifying correctly? But before we even start, we remove some fraction of the data, about 20% or so, as a test, as some testing or validation data. This we do not allow the model to train on. It does not look at it during training. We only test it using this. So notice something interesting. Although the training accuracy is increasing, this test one sort of seems to flatten after a while. Okay. So this is, again, it actually goes back to the same thing about overfitting and the Runge phenomenon and so on that we are doing. After this, what is happening is that the model is sort of fitting to the noise, and its performance on the actual other new data is actually may even be decreasing. So this is another thing that one has to keep in mind when training bigger models, that just because you're doing better and better on your training data might actually means something very bad on new data that you might see. So so that's why when people train, it's very important that they keep some data that the model never sees, so that is what is used to test it, so that they know that it's not fitting to noise. So these checks for whether it's fitting to noise or not, it's again, like, there are lots of interesting questions there. And we can look at we can talk about it later. But here is, like, let's look at some pictures of what the model gets wrong, like what kind of things it gets wrong, because its accuracy is actually pretty high, right? Like, it's like, even on the test data, it's like 97%. I mean, that's a very good score for something that trained in a few, sorry, something that trained within a few minutes. And it got like 67 of these things wrong. So let's see what these wrong ones look like. So here are some of the things that it got wrong. So this one, the correct answer was 2, it said 4, which is maybe excusable. This one, the correct answer was 1, it said 6. Again, that's a bit excusable. This one, the correct answer is 7, it said 9. Here, maybe the correct answer is wrong. I mean, maybe you would say that this does look like a 9. And here the correct answer is 1, it got 8. And this, I don't know what happened. Like, yeah, there's no way this should look like an 8, but still. This 7 and 9, again, excusable. This 5 versus 9, so it predicts 9 and it says 5. Again, you could argue that 9 is what it is really. So you can see that the model actually is not so bad. Like this one, it's the correct answer is 4. It says 2. Again, I don't know why 2. But sometimes it's like really inexplicably wrong, but often it's like not so inexplicably wrong. So, and anyway, it's wrong not very often. So, and this is like the simplest thing to, and it already worked. Okay, so but there's one thing, I moved from the thing that was running on my computer, which is I think still running. It's still running the 10th epoch. To this cloud thing, which was this T4 thing. So what was this T4, and where did it come from? So let's see. Okay, so this thing is something called a GPU, the T4 computer. What that means, the graphics processing unit. Some of you might have seen such a thing, maybe even in school or home or something. The consumer versions of these things look like this. So this is a picture of one of these taken from Wikipedia. It looks maybe more like a bunch of fans than anything like a computer, but let's wait about that. But the funny thing is, why graphics? I mean, where did graphics come from? We were trying to do numbers. We had some matrix maybe multiplying each other, or some numbers multiplying each other, computing with lines. Where did graphics come in? And this is an interesting story. So, when you're so graphics here means this problem of like depicting a scene on your screen. So when the scene may be described in some geometric way, that there are some objects, some before some object is up, some object is in front of some other object, there's a light somewhere, and all of this basically says, so using all of this to calculate which pixels should get lighted by how much intensity and with which color. So these calculations have to be done, and they are constantly being done. Like for example, when I do so if I do this, right, so you probably see my screen with some windows hanging around. So the operating system has to calculate, there are a bunch of windows it has, and it has to calculate which part of which window goes to which pixel. And there's some hardware unit that does this job of then finally rendering it on screen. And that is, the GPUs are basically advanced versions of these things. And their main goal is that instead of doing things pixel by pixel, you notice that the kind of calculations that go on, they actually can handle many pixels at the same time. The same kind of computation is happening on many pixels at the same time. So it runs like this. It runs these kind of computations on several pixels at once. And the important thing that people realized is that the mathematics of rendering pixels of scenes and the mathematics of running neural networks have a lot of similarities. And there's this famous chapter title or quote in the Feynman lectures on physics, is the same equations are the same solutions. Or the equations might be describing elasticity or electrostatics. If the equations are the same, they have the same solutions. So it does not matter what physical phenomena they are describing. If the equations are identical, solutions are identical. And here it's like some version of that if the equations are the same, it does not matter that they are describing graphics or neural networks. They have the same circuits. So that's why GPUs became very important. And this thing is mostly matrix multiplication that's going on. And this is actually an interesting thing, because neural networks in some form have been known since the 1940s. In fact, before many of the other machine learning techniques. Again, and they actually originated in neuroscience. And there's a lot of research on applications, at least in the 80s, even in the 70s a little bit. But till the 2000s, mid 2000s, neural networks were sort of not considered state-of-the-art machine learning methods. Other methods were more prominent, and this was partly because of training and running them was slow, like as you saw what was happening on my computer. I mean, it was not like a very representative example, but this is reasonably representative. Between 2005 to 2012, people realized that graphics hardware could be used to speed up these computations. And this was sort of like the takeoff. At this point, many things happened. Like neural networks started being trained, larger and larger networks started being trained. They did well on many competitions. They did well on many things. Then the AlphaGo, AlphaFold, and slowly, like it started becoming the tail wagging the dog. So earlier it was like graphics hardware was being used for this. Now it's like that GPUs are mostly used for neural networks, and on the side also for graphics. So that's some history. And let me, so this is a math circuit session, so we should have some questions and problems. So let me end up with some questions. So these questions are of a longer duration type than the usual math circuit question. And these are about some basic things in machine learning. So the first one is of energy. So as I said, this picture of a GPU looks like a bunch of fans. So why? Because the CPU generates a lot of heat. If it's generating a lot of heat, so if you remember your thermodynamics and also, it's where is that heat coming from? It's coming from the energy it's using. So it's using a lot of energy. It's using so much energy that if it did not have that fan, then that heat would have melted it or something. So these things consume a lot of energy, much more than a typical computer. And so finding better engineering solutions, better algorithms, this is all left for like you to do. So this is one question. And here's another maybe more philosophical question. So here's an algorithm. It's just one algorithm. Don't try to read it. There's something called the Miller-Rabin test for primality. It's and it very quickly checks whether a number is prime or not. Basically it takes a number as input. It does some very simple calculations, like some modular arithmetic, and then it has this property that if the number is prime, so if it's composite, it will probably at least half. It will say composite. So if n is composite, it will probably at least half. It will say composite. Otherwise, say probably prime. And the nice thing is that its algorithm looks complicated. It's clear, certainly not obvious looking at the algorithm that it has this guarantee that I just said, but we can guarantee with a mathematical proof, and not a very complicated mathematical proof in this case, that it has a very high probability of giving the right answer, and the probability can be boosted and made very high. Okay, so it's a complicated algorithm. It's not obvious that it's the correct algorithm, but there is a proof, easily checkable, which says that this algorithm is actually correct. It will give the right answer with very good probability. And nothing of that approaching this level is possible with any machine learning based solutions, in essentially any machine learning based solution. So, for example, even this perceptron, like one question was asked about like how there are so many different perceptrons. One question one could ask is, which of these is the right one? I sort of skirted the question by saying that, oh, as long as it's giving the right answer, we are happy with one. But we should not be happy with that, right? I mean, we should sort of know why it's doing something, like why it gave a certain answer. In which situations will it work well? In which situations will it not work well? For the perceptron, these questions can be answered because it's just a line, so I know exactly what. Like once the answer is there, I can say what kind of weaknesses it has. But for these larger models, this is often very tricky. It's not clear when they will fail, in what modes they will fail. There are some very nasty modes of failure where there's a picture and the model is supposed to check whether it's a stop sign or not, and some few pixels are changed here and there. To a human, it looks like a stop sign, no change at all, and the model starts seeing it as something completely different, like a go sign or something. And so this idea that like ideally would want that once you have such a thing, you can generate a proof that this is correct under certain such situations. Those things don't seem to don't exist at all. So there's a second problem for all the math circle students. So to end, let me say that very often very foundational advances in science have come from what at the time maybe look like some mundane changes in technology. So like steam engines, actually also a very important invention in technological sense, also led to the development of thermodynamics, which in some sense is arguably the most fundamental thing in physics. I mean, like everything else keeps changing, theories keep changing, thermodynamics remains constant. It's like it's there. And it sort of owes its existence almost fully to steam engines. Similarly, microscopes, like some development in glass, like how optics is done and how glass is grinded and so on, led to a full explosion in microbiology and like so much development in medical science and so on. And so in this era, we have a similar situation that there's a nice engineering takeoff that has happened with these different kinds of machine learning algorithms and GPUs and so on. And the question for you to figure out is, what is the right hand side of this equation here? Okay, so with that, let me stop. Any questions?
Thank you, Piyush. So, yeah, Kanish.
Hi, I had a question. You said that GPUs are used to process graphics and CPUs just calculate, and the maths of both pixels and the math of neural network is same. So we are going to use
It's
GPUs
similar. Yeah,
for
yeah.
CPUs.
Yeah.
Yeah. So, but doesn't both CPU and GPU does mathematical calculations? So how does a
Yeah.
GPU differ
So
from
the GPU
CPU?
so the GPU is optimized for a very specific kind of calculation. So CPU is a general purpose computer. It is supposed to do everything. Like any computation that you can do, a CPU is supposed to do. A GPU is not like that. It's actually optimized for doing some very specific things. In fact, in particular, it's optimized for doing matrix multiplication very quickly, much faster than the CPU. So because it is focused on just doing one thing, it can do it much. I mean, partly because of that, it can be designed to do it much better than a general purpose CPU. A general purpose CPU by construction is supposed to do many things, right? It's supposed to do binary arithmetic. It's supposed to do floating point. It's supposed to like so everything, all kinds of things. And but the GPU is just optimized for doing one thing. So typically, the way the whole thing works is the CPU sets up the computation, then the whole thing is offloaded to the GPU, and it does a quick calculation, and the whole thing is that then comes back to the CPU to do more processing. So that's how it's not like a replacement. It's some symbiotic.
I have a question.
Mhm.
So, like in the handwritten numbers, like it assumed
Which
the
are
model
numbers?
assumed that the the handwritten numbers, like the numbers that
Yeah,
we
yeah,
just
yeah, 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 yeah.
So the model assumed that 3 is to be 9 and 1 is to be 4
No,
or
it did not
something.
assume. It got some of them wrong, and I was just showing you some examples of the things it got wrong. Yeah. So it did
Yeah.
not just assume that, yeah.
What if we can train the model on this data and then kind of
Like you just say that, like, okay, focus more on these things and get them right, right?
yeah, and then
Yeah,
will
actually, yeah,
that
that's a good idea. Yeah.
will the
People do this.
accuracy increase?
Yeah, yeah. So it's hard to predict in advance because by focusing on these examples, you might lose what you had learned earlier. So there's always this danger, right? So it is doing well on the other examples, right? So these are only 68 examples out of some thousands. So there's this danger that by trying to optimize too much on these, your performance on the others might degrade. So whether it will happen or not, you find out by doing experiments. So in fact, this thing also has a name. It's called fine tuning. I mean, like this kind is something like called fine tuning, and it has to be done carefully because of this reason.
Yeah, hi sir. I have a question. In the same thing, I mean, before starting the training, you said that we hide some data and we don't give,
Yeah,
say, we just give 80% of the data for the model to train.
yeah. I think
So
roughly
what are
80%.
the
Yeah.
parameters on which we say that like we choose specific 20% of the data? Because
Oh no, we do it random. Yes, that's important. You choose it at random. So the idea that even so, if you had a specific criterion in mind, then in some sense, in some philosophical sense, you have already given access to the data because that criterion has gone into the choice, right? So already it's already biased in that way. So
but
you choose
by
it at
chance, it might be also the case that all the 20% of the data which we are keeping reserved to check might be the bad data also. So that might
yeah, but
affect.
that's a very rare case, right? I mean, like suppose that exactly 20% of the data is bad or hard or something. If I choose 20% at random, then on average I will have 20% of that 20% that will be bad, right?
Okay.
And changes from that will be very like big changes from that will be very rare.
So so multiple runs of the model, as you said, I mean fine tuning and multiple runs will give the best output which we are hoping for.
Yeah, so no, okay, so multiple runs we don't know. Right? So for example, I showed you this picture that where what was happening is that it already seemed like I was already doing too many runs. Let's see, right? Because so nothing, yeah. So there's nothing here which is always good, right? So ideally I should have stopped here somewhere, like at this point, because after this the performance seemed to be degrading
Downgrading, yeah.
on things it has not seen. So in practice, when people are doing these things carefully, they take these things into account. Like they will track these things. So maybe they will not look like a single downturn is not so big, But if like for three epochs in a row, it is below the previous level, then they stop. So yeah, so many of these things look like yeah, so that's another thing. So before thermodynamics and before calculus and all of these, a lot of like say civil engineering or a lot of mechanical engineering was rules of thumb, right? I mean like make the base like this and the walls like this and it will stand, and if it falls then you say okay, maybe something went wrong, and so there's no theory as such to guide what is happening. A lot of a lot of the things in machine learning are in that stage where uh, not because of lack of effort, it's just hard to come up with a theory to say what will happen. You only find out once you do things. So that is
Okay, thanks.
yeah. Other questions?
Yes, Subrat.
Hi, Piyush. Thanks for a very nice talk.
Hey, hey.
Actually, it's there's not my son is going to ask a question. I'm just here.
Okay,
Yeah.
yes, yes.
I didn't understand what it's doing in the second question you gave.
Sorry, what is the second question? So what?
The
Yeah,
second
please.
problem you gave.
Oh, yeah, okay. The second problem is the problem is this. So I showed you this Miller-Rabin test. It's a short algorithm. It's
But what
not
is
very
it trying to
hard.
do?
Oh, this algorithm. It's checking whether a number is prime or not. Yeah.
Oh.
But the problem has nothing to do with the algorithm. So the algorithm was just to make a point that it's an algorithm which has this kind of an opaque nature that if I first look at it first, I don't even know what it is trying to do. I am not sure whether it is correct. But very quickly I can be convinced. There's a small proof of correctness that this thing is actually correct. It does this detect primality and it does it very well. With machine learning based algorithms, where if I train something to detect digits, can I prove that it will always detect digits of a certain kind, or can I prove that it will like so? Or these days, right? I mean, like many of these things are used to generate mathematical proofs or solutions to math problems. Can I prove that it will generate a correct answer always, or like with high probability? That is the thing that is completely open, and yeah, so it's for you to
The
solve it over the
algorithm you
next
showed.
decades. Yeah, sorry.
Oh, thank you.
Yeah.
Vishank.
Yeah.
Sir, I had a question. Can this machine, for example, even the can the machine ever get fatigued? You give it more number of attempts to run than it actually requires to give the right answer. But
No, so I mean, by fatigue, maybe you can think of this graph as I mean, I don't know, like I don't know if that's what you
yeah,
mean by
the
fatigue,
test,
but
the
yeah, this is
accuracy
like kind of
reaches
yeah.
the accuracy reaches the highest point, and then because it has more number of attempts, it starts degrading in
Yeah, blue thing is rising steadily. So it's like yeah, so it's like sort of fitting to the idiosyncrasies. I mean, like that would be one explanation. But it's fitting to the random noise that is there in the training data, which is maybe not there in the data itself. Like if new data comes, it will be some other kind of noise. Yeah, so it's the same kind of phenomenon as in that current voltage curve, because maybe some point got moved because I don't know, like someone hit the ammeter when I was measuring it, and now suddenly I'm just trying to get that point right, and therefore all my other answers are wrong. So that's the kind of thing in some small way that is going on.
Thank you.
Sir, I also had a question. It's about the model. So the model, to identify what digit it is, it checks the relationships with the other pixels around it in the image, right?
Yeah, actually, yeah, the one I did was like this one is actually doing very little. I mean, like it's not even like yeah. So there's a like kind of cheating here. So it's like the model I wrote here. It does like you can do the following and it will still work, which is miraculous if you think about it. I can take this pixel and I can have a permutation on the pixels in the sense that I can say the like so let's number the pixels from left to right, like these are I think 28 cross 28 images, so 1 to 28, 29 to 56 and so on, like this, and then say pixel number 1 goes to position number 100, pixel number 2 goes to position number 101, in such a way that each one goes to some different place and no two land at the same place, right? So it's a complete scrambling of the image, but I do the same scrambling on every image in the test and the
Okay.
training. This network will not get affected by that.
Okay.
Okay, so in that sense, it's a very stupid network. I mean, of course, the whether a pixel is close to this pixel should matter, but this one is not even looking at that.
Okay, thanks.
So yeah, I was hiding that under the rug, but yeah, the
Yeah.
more advanced ones will actually look at that.
Yeah,
They
we'll
will
take one
do
more
they-
question
Yeah.
and end this at 7:40.
Sir,
Ganesh.
so we are using the training data to train the system. Then what does it even mean to define training accuracy, and how is it different than test accuracy? And what was the
No, so-
axes of the graph that you drew?
Yeah, so here is the thing. So if you look at this code, so there is some full data, out of which some 5,000. So I think there are a total of 65,000 or something. The exact number I've forgotten, but something like 5,000 examples are being treated as test data. They are not shown to the network during training. They are never used in the training loop. So the network never sees whether it did correctly or wrongly when it is computing its values and its which direction to move and so on. Okay, these 5,000 points. Yeah.
But if both the training data and test data are random, won't you expect the training accuracy and test accuracy to be same, because they are both random?
No, they are not
Or
random.
training.
There is a there is
Yeah.
a data. There is some data, right? There are some 65,000 or so data points, out of which we have taken some of them at random, right? I mean, the data itself is not random. Like it's like out of 60,000, you choose some 30,000 at random. So it's still correct data. It's not random data, and the remaining 30,000 you never look at. That's the kind of.
Correct.
Okay.
And what was the axis of your graph?
Yeah, so the axis is, so this x-axis is how many epochs. So like there is epochs, right? Each epoch is going through the whole training data once, and the y-axis is just accuracy. So accuracy is what fraction I got right.
Okay, and the test data is those 5,000 data.
Yeah.
Yes.
Yeah, I think it's 5,000. This picture is from a few years ago when for different.
And the training data, how many data points are there for that?
I think it's
5,000
like
again?
66. Yeah, no, 66, much more. 60,000. I think.
Okay.
Yeah. Yeah, 60,000 in the training and 5. Yeah. Oh, actually, yes. I think what I did was this. The data comes already in two separate points, so 60,000 and 10,000. And yeah, that's so 60,000 is for training, and the remaining out of the 10,000, some 5,000 were being used as this.
Yes, Piyush. Thank you, Piyush, for the wonderful talk and also answering all the questions. And
thanks
to the participants, thanks for joining.
Yeah, thanks, Piyush.
Yeah, thank you.
Yeah, bye.
Bye.